In this lesson, we will be examining the intersection of a line and a plane. In 3 dimensions, there are 3 possibilities for the intersections to occur. The first possibility is that the line intersects the plane at one point, meaning that the system has a unique solution. The second possibility is that the line lies in the plane, meaning that the system has infinite solutions. And the third possibility is that the line is parallel to the plane, meaning that the system has no solutions. Skew lines are 2 lines that do not intersect and are not parallel, meaning that they're in different planes. This also gives no solutions. So in this first example, we need to find the intersection of the line with the parametric equations x equals 1 plus 2t, y equals negative 6 plus 3t, z equals negative 5 plus 2t, and the plane whose scalar equation is 4x minus 2y plus z minus 19 equals 0. So in terms of t, the coordinates of a point on the given line are x, y, z equals to 1 plus 2t, which is your x value, negative 6 plus 3t, which is your y value, and negative 5 plus 2t, which is your z value. So now we can substitute the x, y, and z components into the given equation in order to find the value of t. So we will get 4 times 1 plus 2t, your x value, minus 2 times negative 6 plus 3t, your y value, plus negative 5 plus 2t minus 19 equals 0. So now we can expand the brackets and we will get 4 plus 8t plus 12 minus 6t minus 5 plus 2t minus 19 equals 0. So now when we collect the like terms, we will get 4t minus 8 equals 0. So we can bring 8 to the other side, and for t we will get the value of 2. So now, in order to find the exact point at which the line intersects the plane, we can substitute the t value back into the parametric equations for the x, y, and z components. So for x, we will get 1 plus 2t, which is the equation, and you get 1 plus 2 times 2, which is 1 plus 4, and we get 5 for the x value. Now for y, we have negative 6 plus 3t, so we get negative 6 plus 3 times 2, which is negative 6 plus 6, and this gives us 0 for the y value. And for z, we have negative 5 plus 2t, which is negative 5 plus 2 times 2, which is negative 5 plus 4, and this gives us negative 1 for the z value. Therefore, the point at which the line intersects the plane is 5, 0, and negative 1. Now let's look at the next example. In this question, we need to find the point at which the line with the parametric equations x equals negative 4t plus 2, y equals 4t plus 4, and z equals negative 5t plus 1 intersect with the plane with the scalar equation 3x minus 2y plus 4z equals 2. So this example requires a similar approach as the one before. So first, we're going to write out x, y, z equals negative 4t plus 2, 4t plus 4, and negative 5t plus 1. Now we're going to substitute the x, y, and z values into the equation. So we get 3 times negative 4t plus 2 minus 2 times 4t plus 4 plus 4 times negative 5t plus 1 equals 2. So now we can expand the brackets and we get negative 12t plus 6 minus 8t minus 8 minus 20t plus 4 equals 2. And when we collect the like terms, we get negative 40t plus 2 equals 2. So now we can bring 2 to the other side, and we get negative 40t equals 2 minus 2, which is 0, so t is equal to 0. So now that we know that the t value is equal to 0, this equation is true for all values of t, and any point on the line is a solution. Therefore, the line lies completely on the plane. Now, if we wanted to find out if the line intersects the plane without solving, we can write the vector equation r equals 2, 4, 1 plus t, negative 4, 4, and negative 5. From this, we can see that the direction vector is m equals negative 4, 4, and negative 5, and the normal vector of the plane is n equals 3, negative 2, and 4. We can now find the dot product between them and see if it's equal to 0. So we would do vector m dot vector n equals negative 4 times 3 plus 4 times negative 2 plus negative 5 times 4. This gives us negative 12 minus 8 minus 20, which is negative 20 minus 20, and this equals to negative 40. So since the dot product is not equal to 0, vector m and vector n are not perpendicular. Therefore, the line and the plane are not parallel, and so they must intersect. Now let's do an application question. This question tells us to find the point at which the normal to 4x minus 2y plus 5z plus 18 equals 0, passing through 6, negative 2, and 2, intersects the plane. So to start off, we can find our normal vector, which would be vector n equals 4, negative 2, and 5. And this comes from the equation. So now we can write our vector equation, which would be vector r equals 6, negative 2, negative 2, plus t, 4, negative 2, and 5. And we can also write the parametric equations, which would be x equals 6 plus 4t, y equals negative 2 minus 2t, and z equals negative 2 plus 5t. Now we can substitute the x, y, and z values into the equation of the plane. So we would get 4 times 6 plus 4t minus 2 times negative 2 minus 2t plus 5 times negative 2 plus 5t plus 18 equals 0. So now we can expand. So 24 plus 16t plus 4 plus 4t minus 10 plus 25t plus 18 equals 0. So once we collect the like terms, we will get 45t plus 36 equals 0. And we can bring 36 to the other side, so we'll get 45t equals negative 36, and t equals negative 4 over 5. So now we can substitute the t value back into the parametric equations. So for x, we have 6 plus 4t. So now we would get 6 plus 4 times negative 4 over 5, which is our t value. So that equals to 14 over 5. For y, we have negative 2 minus 2t. So we get negative 2 minus 2 times negative 4 over 5, which gives us negative 2 over 5. And for z, we have negative 2 plus 5t, which is equal to negative 2 plus 5 times negative 4 over 3, which is equal to negative 6. So therefore, our point of intersection is 14 over 5, negative 2 over 5, and negative 6.
So in this case, we're given the scalar equation 3x minus y plus 4z minus 8 is equal to 0, and we're given the parametric equation, And so now what we do to solve for the point of intersection is that we would sub in the x values into this equation, the y values into this equation, and the z values into this equation. So in this case, the x value would be the x coordinate, so the 3, and we're going to be adding the other x coordinate. So that's going to be, and remember that there's a t in front of this coordinate, so you would be multiplying that with that, and that. And so our x would be 3 plus 7t, and our y would be 0 minus 11t, and our z would be 5 minus 8t. And now we would sub that into the equation. So that's going to be 3 times the x value, so 3 plus 7t minus 0 minus 11t plus 4 times 5 minus 8t minus 8 equal to 0, and that's going to give us 9 plus 21t plus 11t plus 20 minus 32t minus 8 equal to 0. And that's, we're going to put all the like terms onto one side. So 21t plus 11t minus 32t is equal to 8 minus 20 minus 9. And now we're going to solve for t. So we're going to add everything up, and we're going to get 0. T is equal to negative 21t. And in this case, we get 0t is equal to negative 21. Since there are no values of t, this means that the line is parallel to the plane. So now we know the normal vector, and now we would have to choose any point q on the plane by selecting arbitrary values for x and y. So let's say if x was 2 and y was 0, I would sub that into the equation and solve for z and make sure that z is equal to 0. So now that we know the normal vector, we would choose any point q on the plane by selecting arbitrary values for x and y. So if x was equal to 2 and y was equal to 0, then z is equal to 0. And so our point would be 2, 0, 0. And now that we have a point that lies on the plane, we would have to find the projection of PQ onto the normal vector, which will give us the distance required. So we know what OQ is, we know what OP is, but we don't know what PQ. But we can solve for what PQ is. So PQ is equal to OQ minus OP. So in this case, OQ would be the vector we just found. So that's Q. Let's just write that down here. So OQ would be 2, 0, 0. And then OP would be the point that was already given to us. So that would be 10, 3, negative 8. And we're just going to subtract, and that will give us PQ. So PQ is going to be 2 minus 10, which is negative 8. And it's going and 0 minus negative 3, and 0 minus negative 8, which is going to be 8. And that's going to be our PQ value. PQ vector. So now that we have the vector, we would now have to solve for the distance from P to the plane. And so we're gonna use this new equation, and that is D is equal to the magnitude of the normal vector times the PQ over the magnitude of the normal vector. And so we know what the normal vector is, so that's going to be 2, 4, -1. And we know what PQ is, -8, -3, and 8 over the magnitude of the normal vector. So that is 2 squared plus 4 squared plus -1 squared. So now that's going to give us, so 2 times -8 is -16, plus 4 times -3 is -12, plus -1 times 8 is -8, over 2 to the power of 2 is 4, 4 plus 16. So our final answer we get is -36 over square root of 21. So therefore, our distance between the plane is going to be 36 over square root 21 in the negative direction.